February 1943, Bletchley Park, Buckinghamshire, England. In the middle of World War II, British intelligence faced a question that no one could yet answer. Could a machine think faster than the human mind and win a war by doing so? By this stage, the Allies were intercepting a constant stream of encrypted German messages. These weren't the familiar Enigma ciphers already being studied, but something far more advanced. The Lorenz SZ-4042 system, used for Hitler's highest-level communications with army commanders. The Lorenz produced a level of encryption complexity that overwhelmed traditional decoding methods. Each message contained thousands of characters, each transformed by a sequence of 12 internal wheels, producing billions of possible settings. Manual analysis was impossible at wartime speed. At Bletchley Park, mathematicians and cryptanalysts, including Bill Tutter and Max Newman, had already achieved a crucial breakthrough. They deduced the structure of the Lorenz machine without ever seeing one. But that knowledge alone wasn't enough. The British needed a way to process intercepted data automatically, something capable of reading, comparing, and testing millions of character combinations every second. That challenge reached Tommy Flowers, a senior engineer at the Post Office Research Station in Dollis Hill, London. Flowers wasn't part of the military or academic elite. His background was in telecommunications, designing reliable, high-speed switching circuits for telephone exchanges. What made him different was his confidence in electronic valves, vacuum tubes that most engineers still considered too unreliable for large-scale use. When Max Newman approached the post office for engineering help, Flowers saw an opportunity. He believed the Lorenz cipher could be attacked using a fully electronic device. Instead of relying on mechanical relays or rotating drums, an electronic system could run continuously at electronic speeds, comparing streams of ciphertext and key patterns far faster than any mechanical alternative. In 1943, the idea of building a computer with thousands of vacuum tubes sounded unrealistic. The general belief was that tubes would fail after a few hours of operation. Even in telephone exchanges, systems rarely used more than a few dozen at a time. Flowers proposed using more than 2,500 when he presented his concept to colleagues and to the government's code-breaking organization, the Government Code and Cipher School, GCCCS. The reaction was skeptical. Funding was denied. Rather than abandon the idea, Flowers decided to build it himself, using post office materials, spare valves, and his own initiative. With a small team at Dollis Hill, he began designing what would become Colossus, the world's first large-scale electronic computer. Every circuit, every relay, and every switch had to be engineered from scratch. There were no textbooks, no examples to copy. Flowers combined his telecommunications experience with new logical design principles to handle high-speed data. The core of Colossus would use photoelectric reading of paper tape. Intercepted Lorenz messages were punched into a continuous strip of paper, which the machine would scan at nearly 5,000 characters per second. The data would then be compared electronically with generated key patterns from virtual wheel settings, searching for the most statistically likely alignment. Each match could identify the probable internal state of the Lorenz machine used for that message. By replacing mechanical motion with electrical pulses, Flowers aimed to remove the physical limitations of earlier code-breaking devices like Heath Robinson, which had been designed under Newman's supervision. That earlier machine used synchronized paper tapes and constantly broke down due to slippage and mechanical wear. Flowers saw that as proof that only electronics could achieve the necessary precision. He worked mostly in secret. Officially, the post office wasn't authorized to build such a device for military intelligence, and his superiors worried about resource shortages during wartime. Still, by the end of 1943, the prototype design was ready. Flowers had personally financed much of the project, spending several £100 of his own savings, a considerable sum at the time, because he believed it would work. The prototype, later called Colossus Mark I, was assembled at Dollis Hill and then transported under tight security to Bletchley Park in January 1944. Installation took several weeks, involving hundreds of cables, racks of glowing valves, and precision-timed reading equipment. The entire system occupied the space of a small room and required a dedicated power supply. Yet once completed, it achieved something no one thought possible: electronic speed applied to logic. When the machine first ran, it processed cipher text from intercepted Lorenz messages in minutes rather than weeks. For the first time, analysts could obtain near real-time intelligence about German high command communications. Operations planners could anticipate movements of divisions and logistics weeks ahead of the enemy. Flowers' success was both technological and strategic, but within Bletchley Park, his contribution remained classified and largely unacknowledged. Official reports credited the cryptanalysts for the conceptual breakthroughs, but made little mention of the engineering behind the system. The secrecy surrounding Colossus meant that even within Britain's scientific community, few knew that a working electronic computer existed before the end of the war. What Flowers had built wasn't merely a tool for code breaking. It was a new kind of machine. It could be configured by setting switches and plugging cables to perform different logical operations. It read input automatically, processed information electronically, and printed results to teleprinters. In essence, it was a programmable digital computer built a full 2 years before any other similar system in the world. The existence of Colossus would remain one of Britain's most closely guarded wartime secrets for decades. Most of the machines were destroyed after 1945, and the few that remained were dismantled or hidden. When public histories of computing began emerging in the 1950s, names like Alan Turing, John von Neumann, and Konrad Zuse appeared. But Tommy Flowers' role was omitted. What few outside government circles realized was that in 1943, an engineer from the post office had already crossed the line into the electronic age. His machine quietly shifted warfare into the realm of computation. The question that opened this chapter, whether a machine could think faster than a human, had been answered, but at the time, almost no one knew it. In the months leading up to D-Day, British intelligence relied on a new kind of advantage, one that didn't fire bullets or drop bombs. It processed information. At the center of this advantage stood Colossus, the electronic machine designed by Tommy Flowers. Within 6 months of its installation, it had transformed Bletchley's most complex code-breaking task into a system of automation. The first version, Colossus Mark I, was operational by January 1944. It used 1,500 vacuum tubes, read paper tape at 5,000 characters per second, and compared intercepted cipher text against thousands of potential key patterns generated electronically. The results were printed and reviewed by cryptanalysts, who could then reconstruct the original Lorenz settings. What once took weeks by hand was now done in hours. For the Allied intelligence network, this meant near real-time visibility into high-level German communications. Lorenz messages carried information directly between Hitler's High Command, OKW, and field commanders in occupied Europe. They revealed the movement of entire divisions, supply chains, and defense plans. Each time Colossus produced a successful analysis, the intelligence, codenamed Ultra, was sent to senior Allied planners, including those organizing Operation Overlord, the Normandy invasion. The improvement was so significant that the British government immediately ordered a second machine. This new version, designed again by Flowers and his team at Dollis Hill, would be faster, larger, and more flexible. Colossus Mark II. It would contain over 2,400 vacuum tubes and offer the ability to electronically simulate Lorenz's 12 wheels, allowing cryptanalysts to test far more settings in less time. By May 1944, Mark II was ready. The upgraded system arrived at Bletchley Park only weeks before D-Day. Its results were crucial. On June 5, 1944, a decrypted Lorenz message confirmed that Hitler believed the Allies would attack at the Pas-de-Calais region rather than Normandy. This piece of intelligence reinforced the deception plan known as Operation Fortitude, ensuring German forces remained concentrated away from the real landing zone. The success of the Normandy invasion owes in part to that single confirmation generated by Flowers' machine. Inside Bletchley, however, Flowers' achievement wasn't celebrated. The environment was strictly compartmentalized. Engineers rarely met cryptanalysts, and few outside the immediate team even knew how the machine worked. For most staff, Colossus was simply another classified tool. Despite the secrecy, the results spoke for themselves. Each Colossus ran almost continuously, processing thousands of intercepted Lorenz messages. Operators fed endless reels of punched paper tape, each carrying raw radio intercepts captured by British listening stations. The reliability of the valves, once the greatest concern, turned out to be one of the system's strongest points. Flowers had argued that vacuum tubes would remain stable if kept powered continuously, and he was right. In practice, failures were rare. The machines ran for months without major breakdowns. In wartime Britain, where spare parts were rationed and every resource was stretched, this reliability was extraordinary. While the Colossus units operated at Bletchley, Flowers remained at Dollis Hill, overseeing the production of new machines. A total of 10 Colossi were eventually built by the end of the war. Each successive version refined the design, faster logic circuits, improved statistical testing, and greater ease of reconfiguration. In effect, they were becoming programmable systems. The technology, however, raised a sensitive question within British command. How much of it should exist, and who should know about it? The Colossus project was classified at the highest level. Even among Allied nations, information about its design was restricted. The United States was developing its own electromechanical code-breaking machines at the Army Signal Intelligence Service, but only a handful of people were aware that the British had already gone fully electronic. This secrecy had consequences for Flowers personally. Despite his decisive contribution, he remained a civilian engineer without military rank. His name appeared on no official reports circulated outside the post office. Requests for recognition or further funding were often rejected on bureaucratic grounds. When Flowers applied for a $1,000 reimbursement for the personal funds he had spent on the first Colossus prototype, the government refused. He was told there was no official record of his authorized involvement at the early stage. Still, the machine's influence extended beyond immediate intelligence. Colossus proved that electronic logic could be used for computation, a principle that would later define the computer age. Its circuits performed Boolean operations at unprecedented speed. It implemented parallel data processing. It used conditional testing to search for statistical patterns. These were all foundational computing concepts, years ahead of their formal recognition. By late 1944, Colossus Mark II was in full operation during the Allied advance across Europe. German communications remained active, but increasingly desperate. As the network collapsed, intercepted Lorenz messages began to reveal the disorganization inside the German command structure. Flowers' machines continued decoding until May 1945, the month Germany surrendered. The Colossus project ended where it began, in secrecy. After the war, all but 2 of the machines were dismantled. Components were stripped for scrap. The surviving units were relocated to the British Government Communications Headquarters, GCHQ, where they were used for Soviet codebreaking during the early Cold War. Tommy Flowers returned to the Post Office Research Station. Despite building one of the most important machines in modern history, he received no public acknowledgement, no award, and no significant promotion. His contribution remained unknown even to many colleagues. The Wartime Confidentiality Act ensured silence. Outside of classified circles, another story was taking shape. one that largely omitted Flowers's role. In the United States, the development of ENIAC in 1946 was widely publicized as the world's first electronic computer. The British, bound by secrecy, could not challenge that claim. For the next 3 decades, the Colossus remained an invisible chapter of computing history. Yet within Bletchley's surviving documents and the testimonies of its veterans, a quiet truth persisted. Without Colossus, the Lorenz cipher would have remained unsolved, and crucial Allied operations might have failed. As post-war computing emerged, few engineers realized that the foundation had already been laid, not in universities or research laboratories, but inside a wartime communications center, by a post office engineer who believed in electronics when almost no one else did. May 1945, Germany had surrendered. The war in Europe was over. At Bletchley Park, the machines that had silently helped end it were still humming. For more than a year, Colossus had intercepted, processed and decoded the highest-level German communications. Now, those same machines were being used to read messages from new adversaries. The world had changed, but the work of signals intelligence had not stopped. For Tommy Flowers, the war's end did not bring celebration. His role remained unknown, his project hidden under strict secrecy orders. The engineers at Dollis Hill who had built Colossus were ordered to dismantle most of the units. Components were burned, manuals destroyed, and designs classified. The decision came from the highest level of the British government. The fear was that the technology, if revealed, would expose Britain's capabilities and compromise post-war intelligence work. Flowers and his team watched as years of innovation were deliberately erased. Only 2 colossi were spared, moved to the newly formed Government Communications Headquarters, GCHQ, at Eastcote, and later Cheltenham, where they continued decoding Soviet traffic during the early stages of the Cold War. The secrecy was total. Even discussing the project in private was forbidden under the Official Secrets Act. When Flowers returned to the Post Office Research Station, his wartime contribution couldn't be mentioned on his record. To most colleagues, he was simply resuming routine telecommunications work. Promotions and funding went to others. In 1946, when American newspapers announced the ENIAC computer as the first fully electronic digital machine, Flowers knew he had built something similar and earlier, but he could say nothing. That silence shaped the next decades of his life. Britain's scientific community moved forward into computing without knowledge of Colossus. Universities like Cambridge and Manchester began building their own post-war computers from scratch. Some engineers reinvented ideas that Flowers had already proven during the war: high-speed logic circuits, photoelectric tape reading, and electronic counting systems. The secrecy also distorted the historical record. When Alan Turing's name became associated with wartime code-breaking in the 1950s, Flowers's work was still under wraps. While Turing's bomb had targeted Enigma, Flowers's Colossus had attacked a different system entirely, the Lorenz cipher, which was technically more complex, but few outside Bletchley knew the distinction. The first computer debate remained centered around ENIAC and later Manchester's baby. The British government never corrected the narrative. For Flowers, recognition might have been secondary to engineering progress, but the lack of acknowledgement affected his career. He continued working at Dollis Hill on advanced telephone systems, introducing electronic switching and pulse code modulation for data transmission. Yet without the visibility of his wartime innovations, he was rarely invited into academic or government computing discussions. Throughout the 1950s and 1960s, Flowers watched from a distance as the computer industry expanded. Companies like IBM, Ferranti, and Univac turned computing into a global business. Each press release claimed new firsts: the first programmable machine, the first electronic processor, the first real-time logic system. Flowers recognized much of it as evolution from principles he had already applied at Bletchley. But the Colossus files remained sealed. It wasn't until 1970 that fragments of the truth began to surface. Wartime restrictions were slowly lifted. Former codebreakers started writing memoirs. Historians began asking how the Allies had managed to read so many German messages so quickly. Declassified documents revealed the existence of a large electronic decoding machine developed at Bletchley Park. But the details were vague. Flowers, now retired, was finally able to confirm his involvement. But even then, many technical specifics were still classified. When the first public articles mentioning Colossus appeared in the mid-1970s, they surprised computing historians. The accepted timeline of computer history had to be rewritten. Flowers gave interviews explaining how he had used 2,400 vacuum tubes in 1943 to create a programmable logic system. His explanations were calm, factual, and consistent with the documentary record that was slowly emerging. For many, it was difficult to believe that such an advanced computer could have existed secretly during the war. By the time the British government officially acknowledged Colossus in 1975, Flowers was 70 years old. Recognition came late, and it came quietly. There were no major awards, no national ceremonies. A small circle of computing pioneers and historians began citing his work, particularly in Britain's post office archives. He received an honorary doctorate from the University of Newcastle and later from London University, but little else. Even then, large parts of Colossus's design remained under security restrictions until the 1990s. The hardware had been destroyed, and only scattered engineering notes survived. Flowers' original schematics had been lost during the dismantling. Yet his memory of the system was so precise that he was later able to assist engineers in reconstructing a full-scale working replica. In 1994, work began on rebuilding Colossus Mark II at the National Museum of Computing in Bletchley Park. The restoration relied on the recollections of surviving engineers and the partial circuit diagrams recovered from archives. Flowers contributed his expertise and verified key design decisions before his death in 1998. The replica, completed in the early 2000s, confirmed the accuracy of his claims. When tested against intercepted Lorenz data, it functioned exactly as described, reading paper tape at thousands of characters per second, comparing key streams, and producing statistical results that matched wartime decrypts. The demonstration settled decades of debate. Colossus had been real, functional, and operational before any other fully electronic computer in history. By then, the narrative of computing had already been rewritten to include Flowers' name. His work was cited alongside Turing, Newman, and Zusi. Historians agreed that while Colossus wasn't a general-purpose computer, it was the first programmable electronic digital machine, the first to use high-speed logic to solve complex problems. For nearly 30 years, the secrecy that had hidden his achievement also delayed his recognition. But once the facts became public, the scale of his accomplishment became clear. Flowers had advanced computing by an entire generation in the middle of a world war. Even after acknowledgement, Flowers remained modest. He described Colossus not as a revolution, but as an engineering solution to a wartime problem. In his words, it wasn't about inventing a computer. It was about getting results faster. The results had changed the course of history. But for most of his life, the man who built the world's first electronic computer could not even tell anyone it existed. Tommy Flowers died at the age of 92. There were no public headlines, no state tributes, and few outside computing circles recognized the depth of his contribution. For half a century, his greatest achievement had remained classified. Only near the end of his life did the world begin to understand how one engineer, working quietly inside a wartime laboratory, had pushed humanity into the electronic age. The rediscovery of Colossus in the 1990s reshaped the early history of computing. Declassified documents revealed that Flowers' design predated all post-war electronic computers, including America's ENIAC and Britain's Manchester Baby. His machine had used thousands of vacuum tubes for high-speed logic, electronic memory buffers, and programmable configurations, concepts that would later define modern computing architecture. For historians, this meant rewriting the accepted timeline of digital innovation. The rebuilt Colossus Mark II, completed at Bletchley Park in 2007, became physical proof. Engineers, led by Tony Sale and supported by surviving wartime staff, reconstructed the machine using period components and Flowers' recollections. When switched on, it performed exactly as he had described, reading punch tape at 5,000 characters per second and automatically analyzing cipher text to find probable Lorenz key settings. The results were measurable, repeatable, and historically verifiable. For the first time, the public could witness a functioning version of the world's first electronic computer. This restoration revived Flowers' legacy. Academic conferences and computing journals began reassessing his influence. The Institution of Engineering and Technology, IET, honored him posthumously, citing Colossus as a milestone in both wartime innovation and the birth of information technology. His name was added to educational exhibits on computing pioneers, and documentaries finally connected his work at the Post Office Research Station with the technological breakthroughs that followed. More than historical credit, the story raised deeper questions about innovation under secrecy. Flowers' invention had been born out of necessity, not theory. Unlike later computing projects driven by academic research, Colossus emerged from an urgent wartime problem, the need to process information faster than any human could. Its existence proved that practical engineering, even under resource constraints, could achieve what formal science had not yet imagined. The secrecy surrounding Colossus delayed progress in British computing by several years. After the war, the government destroyed the machines and suppressed technical details, preventing engineers from building on Flowers' architecture. In the United States, by contrast, ENIAC's public debut spurred immediate research funding and commercial interest. Britain's early lead in electronics was quietly lost to bureaucracy and classification. By the time Flowers' work became public, the global computer industry had already moved on. Historians later argued that this silence changed the trajectory of British technology. If Colossus had been declassified sooner, the foundations for digital computing could have been built in Britain rather than exported abroad. Flowers himself never expressed bitterness over this outcome. In interviews, he described the secrecy as part of the job and said only that he wished others could have learned from the work earlier. Within the broader history of cryptanalysis, Flowers' contribution also marked a shift in how intelligence was gathered. Before Colossus, code-breaking depended largely on human reasoning and mathematical insight. After Colossus, it depended on machine logic, data-driven computation, capable of scaling beyond human limits. Every post-war intelligence system, from Cold War code-breaking to digital surveillance, followed the path he had first demonstrated in 1943. Today, Bletchley Park's Computing Museum displays Colossus as more than an artifact. It represents the transition from mechanical to electronic thought, from wartime improvisation to digital civilization. Visitors see the complex wiring and spinning paper tape, but few realize how radical it was for its time. In an era when most believed electronics were too unreliable, Tommy Flowers had trusted his experience over convention and proved an entire field wrong. Modern engineers studying Colossus note how many of its design principles still apply. The concept of separating logical operations from physical hardware, the use of parallel processing to increase throughput, and the practice of keeping systems powered continuously for reliability all emerged from Flower's wartime experiments. Even his maintenance philosophy, keeping valves warm to prevent failure, anticipated techniques used decades later in high-availability server design. Flower's story also became a case study in the recognition gap between scientists and engineers. While mathematicians like Turing and Tutte are celebrated for conceptual breakthroughs, Flower's exemplified applied innovation, the translation of ideas into functioning systems. Without his willingness to challenge existing assumptions, theoretical breakthroughs at Bletchley might have remained academic exercises. By the early 21st century, Flower's name had begun appearing in textbooks, exhibitions, and national honours lists. The Royal Mail issued a commemorative stamp in his memory, featuring the Colossus circuitry. Bletchley Park's archives formally credited him as the chief designer and builder of the world's first electronic programmable computer. Several computing awards now bear his name, yet the essence of his contribution remains simple. He used engineering to solve an impossible problem. In 1943, with limited resources and no precedent, he built a machine that could process data at electronic speed and change the course of a global war. Colossus did not win battles directly. It provided knowledge that helped shorten the war, save lives, and shape modern intelligence. In that sense, its creator changed warfare without ever holding a weapon. Today, when digital systems govern everything from communication to defense, the principles behind them trace back to that wartime laboratory at Dollis Hill, and to the engineer who proved that electronics could think. Tommy Flowers's legacy is not just that he built the first electronic computer, it's that he showed what happens when practical minds challenge accepted limits. His invention was hidden for decades, but its influence became permanent. The digital age began quietly, with wires, valves, and conviction, and it began with him.